computer. Yes, okay, it looks like I am recording. So welcome to the very fourth workshop, which is on assembly features and design. And the first thing I'll go is mechanical guide. So much like the last one, that we do have part files that are right here. You can access it through the mechanical guide or the public one. Click on the part files. We have one that we're going to use for mates right here. And we're also going to have one that we will use to troubleshoot some errors. So this file does not belong here. It is not. Here it is. Okay. And of course, all the videos so far have been uploaded to YouTube. So I guess let's start with this workshop. So this is the assemblies workshop where we talk about assemblies. This is going to be the last workshop that's pretty content heavy. I feel like if anything, this would be the longest workshop out of them all. And the next two are assembly and part organization, and we have drawings and rendering for the last one. So these are the topics that we'll cover. We're going to go over the assembly process overview. We will go over two assembly methods called top-down and bottom-up assembly. We're going to go straight to SolidWorks, figure out how to start an assembly, mates, some assembly features. We're going to talk about top-down assembly configurations, which also exist in assemblies, assembly analysis, troubleshooting, and how to navigate GrabCAD. Because for this assessment, you're going to have to be able to use GrabCAD if you're a mechanical member. And if you are not a mechanical member, then we also have the file located right in the public folder as well. And I will show that at the very end. This is the exact same thing, what to do during the workshop. I'm just going to skip this because hopefully by this time you should know what you want to be doing. Same prerequisites, unless you're going to skip this slide. So assembly process overview. So this is an example of something called bottom up assembly. And the reason for that is because we start with the parts. We have 4 distinct parts. We're going to add some mates. We're going to create an assembly. And that's generally the assembly process overview. And this example of bottom up assembly, because we start from the bottom, we start with each of the individual parts, and then we make an assembly after we know exactly what those parts are. In this example of some of the mates, concentric, coincident, there's going to be much more. So top down versus bottom up assembly. As you can see from the slides, top down is where the parts are modeled in context with an assembly, whereas bottom up, the parts are made individually and then assembled together. So why use some of these methods? I probably recommend most of the time that you use something called top down assembly. And the reason for that is that when you make an assembly, like 99% of the time, you're not making an assembly just based off of one part. You have to make an assembly that's based off of multiple parts. So for example, if you think about this top piece, it's really connected with this silvery base right here. And you really have to know the dimensions in order to align the holes. Same thing with this shaft. In order to go through this shaft hole right here, the dimensions have to be pretty close together. And for that reason, a lot of the times you use something called top-down assembly, where you need to know the context of other parts. The only reason you'd use bottom-up assembly is if you know the specific designs and dimensions already. And some reason you'd be able to do this is, for example, there's some sites that you're able to have the CAD files already. So something like MasterCard, you're able to pull the CAD files of some certain parts. You don't have to worry about making the parts at all. You already know exactly the parts that you have. You can kind of put it together. I like to think of it almost like a Lego set. You know, in bottom-up assembly, you have all the parts that you need. All you have to really worry about is putting it all together. Whereas top-down would be that you actually have to make the parts yourself. And let's go straight to SolidWorks. So I already have SolidWorks open, so let me just share my screen. So we're going to start right here. So when we get to this screen, so I closed the welcome screen. If you have it there, you could probably go to assembly straight away. Let me go to new assembly. Let me have it open. So when you begin an assembly, you're prompted to insert some parts. So let's go to this universal joint thing. So it's really nice if you have in your file explorer, especially if you're Windows, that when you click a file, you're able to see what it looks like this. So let's insert our very first piece. So you can open it and it'll automatically let you insert it wherever you want. I highly recommend that for your very first piece that you actually click the green checkbox and the check mark. And the reason for this is because it will align the origins, and I can show you that super duper quick. Let me save this. Save this, assembly 1, save. So in this assembly, it has the front, the top, and the right plane, as you probably know, but it also has the origin. It's located right here. And coincidentally, the origin also happens to align. And that is not coincident at all. It's because we click the checkbox, it automatically does that for us. The F right here means fixed. So no matter what we do, the selected component is fixed. It cannot be moved. We can do something called float. It allows us to float around. And notice how the origins are no longer lined up. Origin is right here. Origin right here. The reason you want to keep the origins together is because for symmetry. And you'll see it being used sooner or later. And I accidentally deleted it. So let me add that in again. Here, see, if you're interested in inserting some more components, you can go insert components, browse, connector, pin 2, pin, and yoke. You just drop it down, drop it down, drop it down, and finally drop it on the right side. If you're also interested in inserting multiple same components, you can highlight this and you can click and drag. See how I'm able to quickly add another one. That's also something that you can do. Let's go back. And before you start mates, I highly recommend that if you know exactly where the parts are going to be placed, you kind of move stuff around. You can rotate stuff with your right mouse button. So example, I feel like this is going to be right here. I can move this right here. I'm using my right mouse button, kind of just make the shaft look this way. This thing is kind of be at the top. It makes it much easier when you make stuff, so you know exactly where they are. And this thing, I'm gonna rotate right here. You give me the general location. You don't exactly have to be exact. Let's go on to mates. So the very first thing that you can see is mates right here. It says creates geometric relations between components. In this workshop, we'll cover all of the standard mates, and we'll cover 2 of the advanced mates that I use quite often, something called the symmetric mate and something called the width mate. Feel free to learn some of these other stuff if you're interested in. There's mechanical mates that can be used as well. So let's start the mating process. So coincident mate, it basically means that these 2 faces will be on the same plane. So I'm interested in having this face right here, kind of touching this face right here. I could do something called a coincident mate. So let me do that super quick. I select coincident, I can click, and I can click in here. So based off of that, know that if I were to look straight at this plane right here, look normal, notice that no matter what, if I try to move it, it feels like it's this edge right here is always going to be connected to this edge right here. If we look at it from the other direction, we have a lot more freedom in how we can move it. So that means we need to add another mate in order to confine it further. So the next mate that you can add is you can make these 2 faces basically the same thing. But another thing that we can use is using the power of circles. We can use something called a concentric mate. It basically means that these 2 circles have to overlap. Not most importantly, you don't have to choose just edges. Like I could choose this edge right here. It doesn't have to be edges. I almost usually never choose edges because faces are so much easier to click, click, click. Right here, I can rotate. I also have the ability to lock rotation, as you probably noticed. I can lock rotation, meaning I cannot move it. But I do not want to lock it, so I'm going to unlock. If it's incorrect, you can do something called flip mate alignment, and then it'll mate and it'll kind of correct it if it was super weird. But if not, then you can try to ignore that, which is the reason why I recommend that you position stuff beforehand. Otherwise, that you kind of have to do some extra, the mates will look very weird when you try to do stuff. Okay. So let's look at some of the mates. So we have the parallel mates, meaning that it's going to be very similar to coincident, but it can also mean that these edges or these faces have to be parallel. So example would be this. This face is, let's say, very vertical, and this face is at an angle. I can make these 2 faces parallel. This means that they'll be on the same plane, like this. I can do the same thing for perpendicular. So it would kind of look almost something like this. Let's see if it forces it that way. Perpendicular, click, click. See, just like that, they're perpendicular to each other. I can Control Z to undo. I can see. Next thing I can do is something called a tangent mate. Basically, you need something that's kind of cylindrical in shape, which would be something like the shaft, and you need a basically flat edge. So I'm gonna use this. I can, instead of going to the mate tool every single time, what I always like to do is that once you get very familiar with the mates, you kind of know exactly what you need. So I can click the cylindrical face and I can control click this face. It opens up the mates that I can use. Tangent. So when I look normal to this face, no matter how I move it, it's always going to be tangent to this plane right here, as you can see. And of course, when I look over here, I can kind of move it a bunch of how I want, so it's not fully constrained. Sometimes it can go really out of whack. Let me just delete that. Delete. I think mostly from now on, you will probably see me just, instead of going straight to the mates, I'll be using it. I'll be using click, click, and using this very quick mate way. The reason for that is because it's so much faster, and I'm much more comfortable doing that. So let's continue, except I will go here to show you what the mates do first. So we have the lock, basically lock, locks two components together. It can kind of fix something. We have something called the distance mate. So if I wanted this face right here, where you going? Example. So if I wanted this face, and that is why you need so far away. Move closer. Okay. So first, I'm gonna make it concentric because it's kind of annoying, and you make it concentric, so it moves down too much. Okay. What if I'm interested in having this face be a certain distance from this face? I can do something called a distance mate. Have it be maybe 20 millimeters. Click 20. Check. Now it is stuck there. You can also do something that's called a limit mate, meaning that it doesn't lock it at 20. It means that this is as far as you can go. So we can limit it as 20. We can change some of these parameters, 25, 15, meaning that we can move it to some degree, but not much. It allows us to some, like, if we're interested in like where it should exactly stop and where it should be able to go. Like we want to be able to allow it to move from left to right. We also want to constrain it. It doesn't move left too far. It doesn't move right too far. We can also set things at an angle, but the angles can be super duper weird. So I can click these two. I can do something called angle, and the angle, I can set it to 130. It's very difficult because you might not know exactly what angle it's referring to, but usually it never goes greater than 180. So that's the best thing, is that if it says it's 130, that means that the angle between right here would be, what's number did I use? 130. So this angle would be 130 and this angle would be 50. Even kind of difficult to know what angle they're talking about. So what if I'm very interested in having this shot right here be centered? I could use something in our advanced mates, something called the width mate, also something called the symmetric mate. So the width mate requires 4 faces, 2 from the object that you want to be centered on, and 2 on the object that's going to be centered. For the symmetric mate, you only need 3 faces. Basically, most of the time it's going to be 2 on the object you want to be centered on and 1 face of the object. So let's see if we can do this. So I can click this, click. I want it to be centered on this cube. With mate, perfectly centered. We can use the measure tool to find out. Distance is 38.1. 38.1. Let's see if we can also try to use the symmetric tool. Basically, exact same idea, but the thing is that you require a bit more faces. So let's see if I can try to use a face. So this thing was built symmetric, so that's super nice. So I have my plane, and I can do click, click. I can make it symmetric about these two. Exactly the same thing. You can check. 38.1. 38.1. Symmetric is super similar to width, so a lot of the time, you're probably just going to end up using width instead of symmetric. All right. So let's look at some of the assembly features. So much like normal part features, you have some abilities that you're able to use. So there's assembly features over here. I really almost never use any of this stuff, but it's there if you probably need to use it. I use something more often called, oh, you also have reference geometry if you want reference geometry, of course. You have something called the patterning tools can be very useful. So the very first thing is mirroring. If you're interested in mirroring components, and I can give you some sort of examples on exactly how to do that. So this is something I'm working on right now. Chassis, preliminary model. So I worked on this a little bit more compared to the last workshop. So this would be an example. So I know this piece of extruded aluminum is going to be the same on the other side. So what I can do is mirror it about the right plane. I can choose this to mirror. It automatically does it for us. Same thing, you can also use the linear pattern tool. I have it for this example. So if I were to go backwards, I have this one piece of aluminum right here. I can use the patterning tool, and I was able to create 1, 2. So instead of having a bunch of parts, I'm able to save a bit of time and just have it patterning for me. This is an example of how you would use some of those tools. They are basically the exact same thing in like part and in sketching. Close this. You also have the ability to move components. So if a lot of times you can just click it and drag, looks perfectly fine. You can rotate it from here. So let me show you the other options, but in order to do that, I kind of need to continue sketching this. So I can click, make this concentric, click, let's make this coincident. Sometimes it doesn't pop up, so that can be very annoying. Coincident, right here. Let's make this shaft on the inside, click. So this one can be a little bit special, is that in order to use the width mate, you need faces that are basically flat. But as you can see from this face, it's not really flat. So I guess this would be a pretty good example of when you'd want to use the symmetric mate. So you can click that plane, click, symmetric. So that'd be a good example of when you can use the width mate is when the faces are not flat. So now we have our fully defined. It says underdefined, but we have some rotation that we can remove, but I'm not going to remove it actually. Save. So glue components. So we have free drag. So standard drag is right here. What can be super nice is something called collision detection. Basically means that when we can move it, and if it were to collide with something, it basically tells us. Like, and you can't really hear this, but it basically makes a loud thunk noise. We can try to stop it at collision. I don't think it stops. Stop at collision. But yeah, it says it kind of say the start in collided model. That can be kind of useful if you're trying to check certain things. I only want to check this and this, and this. So with zoom drag, stop at collision. Yeah, it's possible. You also have physical dynamics, which it tries to simulate what exactly, if you were to move one object, how that would change the movement of another object. That's also something that you can do. So so now those are the types of things that you can do in mates. Let's talk about the different types of assembly, top down and bottom up. So this example that I showed you before with different mate stuff, this was bottom up assembly. And the reason for that is because we started with different parts that were already made, and all we had to do was connect them. So let's create a brand new assembly. And let's try to do some default paste are not valid. Yeah, continue. Let's try to do some top-down assembly. So I'm gonna save this and I can save it to. So naturally, you basically start with nothing because this is top-down assembly. You do not have anything to start with. So I think a perfect example would be just like in the multi-body part would be let's make a bookshelf. So go to isometric view. From here, you can do something called new part. Let's call it bottom shelf. Let's start with the bottom shelf. So choose a plane we want to sketch on. I'm interested in sketching on top planes. How about I sketch on the top plane? Center rectangle. This is in millimeters. I have no idea how big this is going to look, but I will pretend that I will kind of pretend that this is a decently sized bookshelf. 300. Let's go 300. Like this. Extrude it a little bit. This seems like a pretty decent extrude. From here, we can exit. So if I were interested in editing the component, I can click it and I can edit component. I won't do that right now. So I have my very first item. I have the bottom of my bookshelf. So let's go right here. I can do new part once again. Let's call it bottom. This would be the side plates. I don't even call it a side shelf. So side plate. I'm interested in sketching right here, so I would do just that. Let me rotate it so it looks a bit more how we view it. And I will use a corner rectangle for this one. So the geometry does matter. So this is kind of why it's called top down. You notice that I have to use the specific corner. Here. Make this collinear. It's a bunch of the normal sketch tools that you end up using. This looks like a pretty decent height. It actually does. That look like a decent height? I feel like it's to be taller. Let's make it 600. Super duper tall. Extrude it. Let's keep it just 10 millimeters. We can have our other side of the bookshelf. And now we can start using some of the easy tools. Mirror components. I'm interested in mirroring across the right plane. I can mirror this component. Super duper easy. I can make a linear pattern. I can choose my direction to be vertical. Components to pattern. This. Up. Pretty decent bookshelf. Now I'm interested in placing a back wall. Let me do exactly that. New part. Back wall. I'm interested in sketching on this space right here. Let me create my back wall. It goes all the way up to here. It's good. I don't want it to be as thick. How about I just have it be 5 millimeters? That's super duper thick at all. So I have my bookshelf right here. So what's pretty nice about this is that you have each of them be its own separate part file. We have a bottom shelf, we have the side plate, and we have the back wall. Example of top-down assembly. Sometimes you have no idea what the dimensions are going to be. So you kind of use this idea of inserting new parts every single time. And you kind of connect everything together. That can be super nice. Now we have this bookshelf. Okay, the next thing that we are going to talk about is something called configurations. And configurations look the exact same thing like they would be in parts. So for example, let's make a configuration. So this is 3 shelves, not counting the bottom one. So let's name this 3 shelves. What if I'm interested in another shelf? Or I'm removing a shelf. So let's call this 2 shelf. This is 2 shelves. You can edit this. So for this configuration, right here, this configuration, I would just have 3, including the bottom one. So notice how I'm able to have different configurations right here. Basically the same idea. You're able to kind of like, even in the same assembly, you're able to add different configurations. It makes it a lot easier that you don't have to basically, like remake it again. Like if I only wanted a bookshelf with 2 shelves, 3 shelves, 4 shelves, I can mess with some of the parameters as well. This is on the assembly level. I'll try to give you an example of one we actually have on one of our robots. Go to grab CAD, Sentry robot, turret, not turret, dual turret. So dual turret. So if I would open this, so in the robots that we work on, we have a bunch of components. So there's some really big assemblies. Sometimes I know on the robot that I used to work on, which is called the infantry robot, we had over 300 different parts. And the reason for this is because not only do we have the plates and the chassis and the frame and all that stuff, but we also model the fasteners because it's a good idea of knowing what type of nuts you need, what type of screws you need, what length screws you need to buy, and it's really helpful. I don't think anything happened at all. Let me try opening it again. There's different options to opening it. If you go to large design review, this is the fastest. You can only see stuff, you cannot edit things. Unless your computer is an absolute beast, I always recommend lightweight, use large assembly settings. Resolved basically means that it uses with all the data, takes super long to load. Let's try to open this again. I do not believe anything is happening. Let's see if I can close this. It appears SolidWorks will not open this. Barrels. Let's see if I can open it in large design review. Very interesting. It will not open. Let me see if I can open the test assembly. So I guess this is the very first, crash or bug that happened. I'm surprised that I did not crash. And that's the one thing that people don't really like about SolidWorks. And I imagine this happens with other CAD software is that there's a probability of it crashing. So let me actually exit SolidWorks and open it again. See if that can change anything. And then in the same way that you can have parts in assemblies, you can also have assemblies in assemblies. And hopefully that I should be able to show you that. So my SolidWorks just crashed again, and I'm hoping that it'll work. Because if not, then that'd be extremely tragic. It is starting. It's verifying. Verifying the license. And that does happen where and that's always why I recommend that when you work on stuff that you save, because it can be very easy for, okay, my SolidWorks open. It can be very easy for your SolidWorks to crash. And especially, I'm pretty sure everyone knows, or everyone should know the feeling of working on something, maybe like an essay, and you completely forget to save, or like your coding, you forget to save your progress if something crashes and you're unable to open anything. So let's see if I can try that one more time. If it doesn't work, then I will try it on a different robot. So let's see. I should also share my screen again. Otherwise, you guys aren't looking at anything. I have so much SolidWorks opened. What am I looking at? Okay, exit, share screen. Do a turret. You guys can see my screen. So this example configurations. So someone called it no barrels within img flip image. You could have it, slip ring. Hopefully you have your names be a lot more specific than this. I have no idea what no barrels mean. Oh, it's loading. So let's go. Looks like it's loading. So like I said, we have assemblies with a bunch of parts. So it might take a while. As you can see right here, this was super quick. It was 76, but it took maybe like 20 seconds already to load. Imagine an assembly with much more components. Then again, it's also my laptop being super slow. I basically used to have a Mac for a really long time, and I finally decided to buy a Caddy laptop off of eBay for like $200, $300. It is super bulky because it's like from, I think, in like the 2000s era. So let's see. Configuration. You can have different configurations, one with the barrel. And for this specific robot, we it currently has it does not have a slip ring. And what the slip ring allows us to do is it allows the upper and the bottom portion to kind of rotate relative to each other. Otherwise, if you try to do that without a slip ring, what can happen is the wires can tangle. So we have slip rings on some of our robots. We're trying to see what this is about. So example of why you use a configuration is that you have two different versions of the robot that you want to use. And this is taking quite a bit of time. And there's errors, as you can probably notice, but that is possible. And it feels like my SolidWorks may have crashed once again. Just loading. Oh, there it is. So as you see, there's a different design. You see stuff moves. I'm pretty sure the person who was working on this, which is who I believe our Century lead, who I believe it used to be Theo, Aiden, and then now it is Richard. So they're no longer working on this stuff. But yeah, the hard thing while working with assembly configurations is that some of the mates might stay the same, so you have to suppress a lot of the mates, or else you get errors super duper easily. Let me just close this. Quickly show you an example of assemblies inside of assemblies. Grab CAD. Let's look at one of this robot right here. I'm gonna go into large design review. So large design view almost always opens it up much quicker. So the stuff that's missing, because I kind of hid components. But anyway, example would be this, is that we have the chassis be its own subassembly. Some nicely labeled folders. Turret base is its own assembly. Turret is its own assembly. And we have the friction wheels have its own assembly. Stuff like that. See, we have fasteners. Only 4 fasteners right here. But there's a lot more. So you can have sub-assemblies inside of assemblies. So the next thing that we need to go to is, let's go back to the universal joint that we just made. Or you assembly 1. Let's look at some of the assembly analysis techniques that we can use. I think my favorite one would probably be something called interference detection. As you notice very easily that this thing is obviously overlapping with this part right here. And when you work with assemblies that are super duper large, what commonly happens is that sometimes by mistake, you might make parts that overlap with another part. So you can use something called interference detection. It basically tells you anything that's interfering, as you can see right here. This piece is interfering, but also something going on right here, something going on right here. I think interference detection is probably my most used assembly evaluator, obviously next to measure and mass properties. Mass properties also work the same way. Measure tool obviously also works the same way. So let's try to go to troubleshooting. So as you probably noticed earlier that, let me open it first, there's, errors can often occur. Let's go to the assembly. We have this thing that I just found online. So you might see a bunch of assemblies that show up, red, a bunch of stuff that's going on incorrectly. And a majority of the time, the super easiest way to fix these problems, and something I use 5% of the time, is just delete stuff. And this only works if you know what's going on. Most importantly, this only works if you know what's going on. But then let's try deleting some stuff. So usually, if you delete the errors, you can just end up putting it back together. So let's see this right here. Delete everything. There's no errors. But notice very quickly that when I try to move stuff around, things can just move, and that's not very right. And obviously, what you can do instead is quickly try to kind of align these back together. So I can click this bottom portion on top of this washer, concentric. Ooh, it looks like a lot moved. So I can click. Sometimes it does not show up. So that's one way of doing it. And sometimes it'll tell you when things break. You kind of have to fix them from there. You can view mates, see what exactly is wrong with some of these components. Sometimes it'll say the selected mate cannot be created successfully. What would you like to do? And usually when you get to those scenarios, it's like, oh, I guess that doesn't work, and it's like you have to do something else in order for it to sort of work. And more errors can show up, but that's something that usually works 95% of the time. Let's try to do something else. Go back to when it was filled with a bunch of errors right here. So you can click the mate group, do something called mate exploit. You could diagnose the problem. It basically tells you what's wrong. It says right here, it's coincident mate. The planar faces are parallel, but their alignment is reversed. Okay. Diagnose. Okay. And usually just messing with this, it'd be like coincident mate. The components can't be moved to position which satisfies this mate. Planar faces are not coincident. Oh, planar faces are not coincident. How about we just suppress this for now? Diagnose. And you kind of mess with stuff from here if you kind of want to continue messing with stuff from here. What you can also do is look over here, analyze this problem. Subset 1. What is wrong with this? So we have this coincident mate, we have this concentric mate, we have this coincident mate that no longer exists. And you could what you could always try to do is just keep on messing around with this type of stuff. It's like, like in order to figure out what exactly is wrong, you can mess with, you could toggle alignment, diagnose, is it gone? It's not gone. And you can try to do a bunch of stuff in order to try to fix things. Some of them would be an extremely slow process. So like always, instead of deleting everything at once, I recommend that you delete things slowly. So usually if the maze is overdefining the assembly, we can delete stuff. Anything move? Oh, okay, looks like nothing was wrong there. This maze is overdefining the assembly. Delete. Okay, looks normal. Let's delete this. Oh, there's some movement right here. That does not look right. So let me just Control Z, Control Z. So these spaces have to be normal. So I believe that is something we need to fix. So let's see if put it back together, see if anything happens. No. Let's make it parallel. So that might be an issue, as we can see it kind of slides. So our goal would be to figure out how exactly we can get this thing to be normal. So we try to move it around, nothing much happens. So right here. So let's see what's wrong with this component. View mates. This thing is also really wrong. Let's delete this. And a bunch of other mates just went kablam, which is super duper, which is funny like always. So this could be a very like long process when you're trying to troubleshoot things. And this sort of problems really only happen when you mess like the first thing is that when mates come up, you should fix them right away. And it can be a very tedious process, but like it takes quite a lot of time, but slowly and eventually you'll be able to fix things. Which is why a lot of the time you try not to use too many mates at the same time, which is why I think that having these mirror tools and padding tools, usually they don't end up breaking, and that's a very hard usually. And so you usually don't have to mess with time with some of the stuff. Like I can just quickly go through here. And once copy moves to position satisfied, I'll play, but the boost is wanting the correct orientation at this main change the alignment setting. Flip mate alignment. Oh, I got that fixed. Oh, looks like everything is sort of fixed. Okay. See, and sometimes you get this very stroke of luck where you're able to just like, maybe you fix one thing and everything just gets fixed at the same time, which is super duper cool. Okay. Let's get these two things to be connect. Okay. I think other than the fact that this thing kind of hits it, which I believe that is not very good. So let's see if I can change some of these mates. These two have to be. But yeah, that'd be an example of how you would troubleshoot stuff. Obviously, there's more errors that you can kind of fix, but I don't want to be on this for too long. And your goal is, I guess at the very least, is to not have any errors or warnings at all. We save this. We're able to process. Close. The last thing that I do want to show is going back to our universal joint example. It's something called smart mates. So a smart mate is a way of just doing things super duper quick. So let me actually destroy all of these mates. Move, move, move. As you probably know that I can, click and click to automatically have the mates line up. I also do something called a smart mate. So I can click something and I can hold Alt and it automatically kind of attaches it for me. Boom, right there. Let me try to do the same thing. I can attach this. Boom, connected, right there. It's just a faster way of doing things. Its most common use case is when you want to add multiple mates at the same time. What if I'm interested in making this edge not only concentric with the shaft, but also have the face touch the face of this block right here? Let me see if I can try doing that. I can Alt, click. Okay, is it possible? I have to aim it. Oh, there it is. See, with one tool, I'm able to quickly add the concentric and the coincident mate. So that's when I usually use smart mates when I work with fasteners, because with fasteners, you always want it to be coincident to a face and you always want it to be concentric to a hole. Otherwise, sometimes I like taking the time to really put one mate at a time. And see, the main difference with SolidWorks and certain CAD softwares like NX 1984, Fusion 360, and OnSketch, which I believe is what it's called, is that you have a lot of control over mates. In mates and some of the other CAD softwares, they combine coincident with concentric. And with SolidWorks, it feels very low level. You can do a bunch of different stuff. You have a bunch of different mates. And what people don't really like about that is sometimes you get mates that stretch on for a super long time compared to other programs where the mates are basically one mate does multiple things. So this means that there's less chance of error. Because when SolidWorks, obviously, the more mates you have, that means the more error that you can have in your assembly. And that'd be kind of like the biggest difference between, other than the user interface, of course, it'd be the biggest difference between using something like Fusion 360 compared to using something like SolidWorks. So let's go on to GrabCAD. So at the end of this workshop, I'll try to see if I have any files in the other CAD softwares, and I can quickly try to show you how mates look over there, so you can have a decent idea. Let me stop screen sharing. I'll go over GrabCAD in more detail in tomorrow's workshop, use it for organization. So GrabCAD, when you log onto GrabCAD, we have our Try2 Robotics thing. So with GrabCAD, we're able to, when you open it, for example, this would be an infantry project. You could have files, you could have folders, a bunch of different stuff. I have more familiarity with something called this is the robot that I worked on. You're able to make changes. You can have comments as well, like this, changes to the battery, shooting an electronic shield. It feels very similar to like sending commits to GitHub. You can commit stuff, you can add comments. You have folders, a bunch of folders. Nothing is showing up right here. Prototype 2, chassis. You have basically all your files right here. Let's see. And then the most important thing that we like about something like GrabCAD is it has version control, which I'm pretty sure is something like Git also does as well. You see how you're able to have different versions? In my comments as well. If you have, if you upload stuff, you upload a new version, you don't have to say, oh, part version 2, part version 3. GrabCAD automatically does it for you. If you're interested in moving back to a different version, like rollback, and you're able to restore. You can also download different stuff if you want to look at it. Let me now share my entire screen. If you do use GrabCAD, then I highly recommend that you actually use the browser app, which I have downloaded right here. Using the browser app, you're able to create a local folder, and you're able to upload stuff, add any comments. You're also able to download anything that you need. It's basically a very easy way of being able to solve illusions. I'll go a little bit more on it tomorrow. And share. Let me go back to my normal screen. And the application that you need to use this for is that we have something called the Common Parts Library. Common Parts Library, where are you? Basically, all the parts that we use in the club basically that we have compiled into a single location. So if you need to switch anything, you can use the switch bar. Like I'm interested in switching for something called the large armor module. It shows up right here, large armor module. The port names and assembly names are different. See, this is SolidWorks part, this is SolidWorks assembly. And I believe in your assessment, let me look at this super quick. Right here, top down, bottom down, what does the width mate do, which is fall down assembly feature. Right here, it says right here that you'll need access to the rules and the common parts library because you need to be able to find something called the main control module. So you can just easily switch that up. Main control module. Main control module right here. You're able to, this is super slow, but if you give it enough time and it's a very quick part, it loads up. And then, how to put your exact value for the center mass. All right, that's right. So for center mass, you're able to look at your mass properties and you're able to look at center mass. And the most important thing that I mentioned right here is to make sure that the origin of the assembly is coincident with the origin of the main control module. Some drawing stuff that you can look at. Like this, you can kind of see the model right here, which is really nice. Using GrabCAD. And that is basically the end of this workshop. So if there's any questions, I'll answer that. And then if there are no questions, then I'll see if I can have either Fusion 360 or NX 1984 up and running. I'll show you how assemblies look on there.
Yes. So is there like a specific like pattern of like test like method to root out these errors potentially?
No, not really. The really only way is to, so there's one way that you could do something called delete all that I showed, but the problem with deleting everything is that usually it fixes the problem. But then what happens is that stuff can move around. If you know exactly how the stuff kind of connects together, usually this works well because you know how parts connect. But if it's a part you've never seen and errors show up, then you have no idea how to fix these errors because you have no idea like what's the design intent? Like, how are these supposed to be mated together? Should this be, coincident? Should these be put at a distance? The second way is basically doing it one at a time. I think that always works out pretty well. You basically fix one problem, like, is it fixed? Then you work on the next thing, you work on the next thing. Basically trying to isolate one error, trying to solve that one error works out well most of the time. Like, and of course, and I always mention that, like what people don't like about SolidWorks, it's just the errors that come with it, mainly because, like you have the freedom to make these mates, and there's a bunch of mates that you can do. And by having a bunch of mates, when one thing breaks, this error usually propagates and causes a bunch of errors because parts are just so interconnected that when one thing is wrong, then a bunch of stuff that are kind of connected to each other end up becoming wrong. And that's why people really don't like SolidWorks. But I guess it is a trade-off for being able to have like this level of control with mates.
Oh, for making parts, then is there like a ability to like if the parts are at like a wrong angle, does it like automatically like align it?
Wrong angle. So what do you mean by wrong angle? Does it mean that you want it to be coincident? Like maybe there's a face right here, there's a face right here. Do you want them to like connect like this? Or what do you mean by wrong?
Like there is like a sort of like a slot for like a shaft to go through, but then the shaft is like a 90-degree angle offset to it. Does it like automatically do that rotation to like fit inside?
Okay, I think I know exactly what you're talking about. Let me see if I can actually model it. Okay, I think I have a pretty decent. And then if it's not correct, then make sure you correct me. Okay. So let me make the part first. So I believe that I'm gonna create if it loads. Come on, come on. So I'm gonna create the part. So it's just gonna be a simple rectangle. It doesn't really matter. I kind of just need the hole to be specific. Make this 10. And also I can also make a slot because I'm feeling kind of cool. Click, click, 10, extrude, good enough. If I want it there, let's call it there. I call it slot. I can make an assembly from this part. Assembly. Place it right smack in the middle. Assembly, SM4. And then I can make another part. This, which is basically a way of just, this is a quick way of just doing bottom up assembly. I know exactly what parts I want to make, so I can just create the parts in their own separate file. Hopefully these are millimeters. It's always been in custom, so I'm just hoping that like I've been using 10. Hopefully that the units match. I'm just kind of hoping. I'm just really hoping that they match, but okay. I have my shaft. I have the thing I want to go into it. So let's browse. Part 2. So what you're asking is that if I were to, I do not want it fixed. Okay, flipped. So if this would not be. So 90-degree angle would be like this, and I'm interested in putting this shaft inside of the slot, right?
Yes.
So let's see what happens. It honestly does it. So it's in fact true. Let's try it for the slot. Same thing. Let's see if it works with the tangent mate. The tangent mate actually does mess up with the tangent mate. So sometimes you really do have to like rotate it for it to work. Like if I were to make this tangent with this now it actually is kind of tangent compared to the super duper weird way, where if you have it like this, and I make this tangent to this, see how it kind of like, it's not perpendicular, it's kind of parallel with like this. So orientation does matter, but usually for concentric stuff, it works out pretty well. And the reason for that is because it's very specific. With the coincident mate, what you can have an error with is that it does not know which face you want to do. But with a concentric mate, it knows that you want these two circles to align, and it works out pretty well.
Oh, okay. Also, for like in the previous sessions, like and when you mentioned about shelling a body, is it possible to have like to shell a body but not have like an open face, like have a hollow shell internally?
Okay, it is possible. Let me see if I can try that. So let me go close. Yes, close. Okay, let's see if I can shell this then. Okay. That was obviously not it. Okay, shell. Okay. Let's go 2 millimeters. Click this. So if you would just click a face normally, it would remove that face, which is obviously not what we want to do. So how about we do something called shelling outward? What does shelling outward do? It also does not work. I believe you're able to do that. I would have to switch up, which is pretty normal that if you aren't sure about what to do, that, I don't know everything about SolidWorks. There's a bunch of stuff that you can do with SolidWorks. And a lot of the times you have to switch up how to do it. So let me actually just show you what I'm looking on right now. Is that SolidWorks usually, like same problem with code is that if you have a problem with code, that you just go straight to Stack Overflow. You just type it in with the Google search bar. Same thing can probably work here, how to hollow out a part. Usually watching videos works out pretty well. And like you probably see it says hollow out your part with the shell feature. This is LinkedIn. Usually I look straight at a YouTube. I don't think this even helps. Yeah. Usually you look at a YouTube video and see exactly like how to do it. This is a super long video for trying to show something. And usually try to see the best, like what can they do. Click, let's see what he does. I have a pretty good feeling that he doesn't, in fact, actually I have no clue. Does he actually end up being able to do it? Okay, he has a circle. Oh, so he's actually, I think he was actually able to do it with the sphere. I have a feeling he just clicked the. Wait, let me just see what he does. But yeah, this is what happens a lot of time. If you have no idea how to do things, oh, I guess he didn't. Wait, did he? Move on. So a lot of the times that you're not really sure that. Oh, I guess he did Andrew Charlotte. I guess. Oh, maybe not. But a lot of the times you won't know exactly how things work in SolidWorks, and you will have to switch stuff up. Like it happens a lot of the time. But like I'm pretty sure it is possible. But the problem is that I have no idea how to do it at the moment. I can always try to figure it out and try to get back to you if you are still interested.
Oh, okay. Uh,
You know.
oh yeah, thank you.
Okay. Okay. I'll keep. Uh, let me see. I'm opening Fusion 360. What's this? So even though we use SolidWorks in the club, like no one actually teaches you SolidWorks if you are a mechanical engineering major, which is really interesting. You use something called Fusion 360 that they do teach you. And I have asked why they taught it to us, and they said that it's kind of like the new hip way, which I don't, because they used to teach Inventor, and I guess that was super interesting. So on Fusion 360 uses cloud-based, it's cloud-based, so it requires an internet connection. SolidWorks does not require an internet connection. So that's also the reason why we have to use GrabCAD is because SolidWorks by itself doesn't automatically connect to the internet. Well, something like Fusion 360 does. So let me see if I can load this up. And do I have Fusion up and running? It is. It's slow. Is that? While I'm here, I'll also show you the different interfaces of stuff, which I think is also pretty nice to know. Sorry that if this thing's going a little long. You see that you can make sketches right here. You have something called extrude, revolve, hole. So this is an example of where they have the extrude stuff basically be the same thing. See how you can join and cut a little bit different. The feature manager bar is down here. There's some stuff that you can learn right here. So see, I can have all my parts are just on the web. I don't have to worry about anything. So let me see if I can do this. Show you some of this. So this is an assembly. Oh, I call it, and it does have automatic version control. So whenever you save something on here, it automatically updates the version, which is why if you look down here, you see version 263. I'm someone who saves a lot. So the fun thing about Fusion 360 is that it saves hella. So that means that you're basically able to, there it is. So it saves hella, so you're able to essentially have like a bunch of different like versions, even though, okay. So mates down here. Oh boy. So so for these mates is that if I actually so where are you? Assemble. Joints. So they have something called joints and this has motion. So they have something called rigid, which locks components together. So you probably need like 3 coincident mates in order to make this. They have something called revolute, which rotates, which is pretty similar to concentric, but you also have the ability to kind of connect stuff together. This also means that it's kind of like a coincident and a concentric mate at the same time. There's something called a slider, which is very similar to tangent, cylindrical, pin slot. See, you basically only have like these mates and this is everything that you need, and SolidWorks kind of separates them out into like different stuff that you can do with. So rigid can just lock stuff. So this would be an example of like a revolute. See, like it basically, like able to control stuff. So that would be something like Fusion 360. Some of the tools are very similar. You can measure stuff. You can, construct different planes. You just other different stuff you can do as well. That's Fusion 360. And that's something that they'll actually teach you if you are a mechanical engineering major. If you are in structural engineering, then I believe that they actually teach you SolidWorks. I do not know if you're an aerospace engineer. If you are an electrical engineer, I believe actually I believe you use something browser based because for a class that's EC5 and they make you use something browser based. I do not know which CAD software you use, but I know that CAD can be offered from the browser. Let me see if I can find another example. Okay. Right, because there's another example. So I've also had experience with something called NX 1984. So the user interface is obviously so much different. You basically have there's something called the part navigator. There's something called the assembly navigator. Basically, the feature manager stuff is just basically all right here. You notice that very similar stuff. You can create planes, you can create sketches, you can extrude, you can revolve, you can create holes, you can create chamfers, you can shell, patterning, mirroring, bunch of stuff like that. Analysis, you can do measure stuff. So I made this mount, very basic mount right here. You make constraints. So here are some of the constraints that you can see. Fit. Fit is very similar to coincident, but also is very similar to touch. So basically, a lot of the times you have very similar ideas of different CAD software. They have different sort of tools, and let's see if I can actually show some of this stuff. I in fact do not know. Oh, here. So, but yeah, there's like all category of softwares are pretty similar. Assembly constraints. Let's see something. Let's see if I can find some constraints. So you have a little bit more options. So the touch constraint, constraints to objects that touch align with other. This is basically the same thing as coincident. Concentric is still here. Distant mate is still here. Fixing is fixing. Parallel, perpendicular, align lock. Fit constrains two objects with equal radii. So it looks like fit is used mostly for circular stuff. Bond is it feels like a better coincident. You have center, which is basically the same thing as width or symmetric. So stuff does show up. They might have different names. You have angle. You have some of the joint stuff that you can do. You see the UI is very different. And sometimes you might be wondering, what CAD software should I use? Well, I think a lot of it also depends on industry. Like NX is very commonly used in the aerospace industry. So if you're looking to get into like NASA, SpaceX, stuff like that, they use NX more often. And SolidWorks is just an industry standard, but then that's also, even though it's like that, it's like some companies use it, some companies don't use it. So it's like it's so standard that some people like to go for more specific stuff. Fusion 360 is very commonly used for hobbyists because it's free. There's other CAD softwares that people like to use because it's free. I guess it might try something, see how you like it. You will kind of like think about it, and if you feel like it's kind of uncomfortable, you can try to go on to a different CAD software. And that is the final end of this workshop. Just showing you some of the different CAD softwares and how assembly mates work in those. Right, time for me to stop this recording.